In 1969, a rancher named Rod Wells was walking across his property in the Naracoorte Caves of South Australia when he noticed something odd. A small opening in the limestone, barely wide enough to squeeze through, led down into darkness. Wells was curious. He grabbed a flashlight and lowered himself into the cave. What he found at the bottom stopped him cold. Bones. Thousands of them. Piled in drifts across the cave floor like some ancient graveyard. Skulls the size of basketballs. Femurs thicker than baseball bats. Jawbones lined with teeth as long as human fingers. At first, Wells thought he'd stumbled onto some kind of mass die-off. Maybe a drought had driven animals into the cave seeking water. Maybe a flood had washed their remains underground. But as paleontologists began excavating the site over the following decades, they realized something far stranger. These weren't the bones of a single catastrophic event. They were the accumulated remains of hundreds of thousands of years. Layer upon layer of extinct megafauna that had fallen through sinkholes in the cave roof, unable to escape. And the species they found were unlike anything walking the earth today. Giant wombats the size of hippopotamuses, marsupial lions with retractable thumb claws, kangaroos standing 10 feet tall, monitor lizards longer than crocodiles, flightless birds that could sprint at highway speeds and kill with a single kick. This was Australia during the Pleistocene epoch, roughly 2.5 million to 700 years ago. A time when the continent was ruled by creatures so massive, so bizarre, so perfectly adapted to kill, that the landscape itself became a proving ground for survival. News of the Naracoorte discovery hit the scientific community like a thunderclap, because here was physical evidence of an entire lost world. A world where being big wasn't just an advantage, it was a requirement. Where the food chain was inverted. Where the prey could crush you and the predators could disembowel you with a flick of their wrist. Prehistoric Australia wasn't just dangerous. It was the most hostile environment for mammalian life that has ever existed on any continent. And if you'd been dropped into that world as a human, your chances of survival would have been essentially zero. So here's the question. What made prehistoric Australia so impossibly deadly? Why did evolution produce monsters here that make modern apex predators look tame? And what does the extinction of these megafauna tell us about the fragility of even the most dominant species? To understand that, we need to go back, way back, to when Australia first broke away from the rest of the world and began evolving in complete isolation. Here's what most people don't realize about Australia. It's not just geographically isolated today. It's been isolated for an incomprehensibly long time. Around 180 million years ago, Australia was part of a supercontinent called Gondwana, connected to Antarctica, South America, Africa, and India. But starting about 96 million years ago, tectonic forces began tearing Gondwana apart. Australia and Antarctica separated from the rest around 45 million years ago. Then, about 30 million years ago, Australia finally broke free from Antarctica and began drifting north toward the equator. Think about what that means. For the last 30 million years, Australia has been completely cut off from every other major landmass. No land bridges, no migration routes, no genetic exchange with the rest of the world's fauna. It became the ultimate evolutionary laboratory. A continent-sized petri dish where life could experiment with body plans and survival strategies that would never work anywhere else. And here's the thing. When Australia split off, it took with it a unique cast of characters. Marsupials, monotremes, and very, very few placental mammals. See, on every other continent, placental mammals, animals that give birth to fully developed young, came to dominate the ecological landscape. Lions, bears, wolves, elephants, primates. These are all placentals. But in Australia, marsupials, animals that give birth to underdeveloped young that finish developing in a pouch, had the continent to themselves. Without competition from placentals, marsupials radiated into every available ecological niche. Need a large herbivore. That's where Diprotodon came in, the largest marsupial that ever lived. Picture a wombat scaled up to the size of a white rhinoceros. 3 meters long, 2 meters tall at the shoulder, weighing up to 800 kilograms. That's over 6,000 pounds. Diprotodon had a massive, barrel-shaped body supported by pillar-like legs. Its skull alone was nearly a meter long, with forward-facing incisor teeth that could strip bark from trees and massive grinding molars for processing tough vegetation. It moved slowly, like a living tank, browsing on shrubs, grasses, and leaves across the woodlands and grasslands of Pleistocene Australia. For context, modern wombats, Diprotodon's closest living relatives, max out at about 35 kilograms. So Diprotodon was roughly 80 times heavier than its modern descendants. But here's what I find fascinating. Diprotodon wasn't some isolated oddity. It was just one member of a diverse megafaunal community that included dozens of species, all operating at sizes that would be impossible in today's Australia. There was Pleistocene, another giant marsupial that looked like a bizarre cross between a ground sloth and a tapir. It stood about 2.5 meters tall and weighed around 1,000 kilograms. It had a long, flexible trunk, like snout and massive claws for pulling down tree branches. There was Zygomaturus, a relative of Diprotodon that was slightly smaller, but just as bizarre. A heavily built marsupial with a deep, compressed skull and unusual nasal structures that may have supported an inflatable nose for display purposes. And then there were the giant kangaroos. Not like the kangaroos you see today. These were short-faced kangaroos of the genus Prehistoric. They stood up to 3 meters tall, that's nearly 10 feet, and weighed up to 240 kilograms. But here's what made them truly alien. Modern kangaroos have long faces and relatively small forelimbs. They're built for speed and agility, hopping at high speeds across open terrain. Short-faced kangaroos were different. They had flat faces forward, facing eyes like a primate, and powerful forelimbs with 2 elongated fingers ending in large claws. Scientists believe they were browsers, not grazers, using their height and claws to pull down high branches that other herbivores couldn't reach. Imagine encountering one in the wild. A kangaroo taller than a basketball hoop, staring at you with binocular vision, capable of standing upright and manipulating vegetation with hands that could probably disembowel a predator if threatened. So with all these massive herbivores lumbering around, you'd expect there'd be equally massive predators to keep them in check, right? Well, here's where prehistoric Australia gets really interesting. Because the apex predator of this entire ecosystem wasn't a mammal at all. It was a bird. Meet Juniornis newtoni,
Keep it low through here, mate.
a flightless bird that stood over 2 meters tall and weighed up to 250 kilograms. It belonged to a group called Dromornithids, the thunderbirds. And while scientists still debate whether Juniornis was primarily herbivorous or omnivorous, its sheer size and powerful beak made it a force to be reckoned with. But Juniornis was just one of several large flightless birds that roamed Pleistocene Australia.
Megalania.
There were also smaller,
reptilian starvation,
faster species that could sprint at high speeds and deliver devastating kicks with their powerful legs. Think about it this way. In Africa, large herbivores are kept in check by lions, leopards, and hyenas. In North America, it used to be saber-toothed cats and dire wolves. In South America, terror birds and giant carnivorous marsupials. But in Australia, the predators were weirder. The real apex predator, the creature that sat at the very top of the food chain, was Thylacoleo carnifex, the marsupial lion. And this is where prehistoric Australia crosses the line from dangerous to utterly nightmarish. Let's talk about Thylacoleo, because this animal represents everything that made prehistoric Australia so uniquely terrifying. Thylacoleo carnifex. The name literally means pouched lion executioner. Was the largest carnivorous mammal to ever exist in Australia. It was about the size of a modern African lioness, weighing between 100 and 160 kilograms, roughly 1.5 meters long with a shoulder height of about 75 centimeters. But here's the thing. Thylacoleo wasn't just big. It was mechanically optimized for killing in ways that make modern big cats look inefficient. Let's start with the bite force. Biomechanical models suggest that pound for pound, Thylacoleo had the strongest bite of any mammalian predator that has ever lived. Its bite force quotient, a measure that accounts for body size, exceeded that of modern lions, tigers, and even hyenas. How? Well, the answer is in the skull structure.
Got it rolling now.
Thylacoleo had an extremely short, broad skull with massive zygomatic arches. Those are the bones that form the cheek region and anchor the jaw muscles. These arches were so enlarged that they gave the skull an almost alien profile. More surface area for muscle attachment means more crushing power. But here's what makes Thylacoleo truly unique. Its killing tools weren't its canine teeth. Those were reduced to small pegs, almost vestigial. Instead, Thylacoleo killed with its incisors and molars. The incisors were elongated, blade-like structures, essentially biological knives that could slice through hide and flesh with surgical precision. The molars were modified into carnassial shears, similar to what you see in modern cats and dogs, but even more specialized for cutting rather than grinding. Think about it this way. Most predators bite and hold. They rely on suffocation, blood loss, or shock to bring down prey. Thylacoleo probably killed by inflicting massive, catastrophic wounds. Those blade-like incisors could sever major arteries or slice through muscle groups, crippling prey almost instantly. But wait, it gets better. Thylacoleo also had a semi-opposable thumb. Not just a dew claw like modern cats have. An actual functional thumb with a large, retractable claw that could extend up to 6 centimeters. Scientists believe Thylacoleo used this thumb claw for grappling with prey. Picture it. A 150 kilogram marsupial lion lunging from ambush, hooking its thumb claws into your back or flanks, pulling you down, then delivering a killing bite with those blade-like incisors. And here's the kicker. Thylacoleo was likely a solitary ambush predator. It didn't chase prey across open plains like lions do today. It stalked. It waited. And when it struck, it did so with overwhelming force and precision. Fossil evidence suggests Thylacoleo was also an adept climber. Its robust forelimbs, strong claws, and flexible spine indicate it could scale trees and rocky outcrops,
These bubbles contain the
environments where many large herbivores sought refuge.
And the methane
So imagine you're a
levels correlate with the
Diprotodon.
drought data from the
You're massive,
Australian
slow-moving, and relatively safe from most threats, just by virtue of your size. But you're not safe from Thylacoleo, because Thylacoleo doesn't need to outrun you. It just needs to get close enough to sink those claws in and deliver a killing bite. Now, here's the question everyone wants to know. With all these giant herbivores and terrifying predators, how did the ecosystem even function? What did these animals eat, and how much? Well, the answer depends entirely on understanding Pleistocene Australia's climate and vegetation. Because the Australia of 50,000 years ago was nothing like the Australia of today. During the Pleistocene, Australia was cooler and, in many regions, wetter than it is today. The continent supported vast grasslands, open woodlands, and pockets of dense forest, particularly along the coasts and in the southeast. This was a mosaic environment. Not a single uniform biome, but a complex patchwork of habitats, driven by rainfall patterns, fire regimes, and topography. In the interior, you had semi-arid grasslands and scrublands dominated by drought-resistant plants. Along the coasts and in river valleys, you had more productive woodlands with a mix of eucalyptus, casuarina,
Jawbone.
and flowering shrubs. And here's the critical point. This environment was rich enough to support megafauna, but marginal enough that those megafauna were always operating on thin ecological margins. Let me explain. Large, bodied herbivores like Diprotodon and Pleistocene needed enormous amounts of food. A creature weighing 800 kilograms, probably consumed 100 to 200 kilograms of vegetation per day. That's the equivalent of a small tree's worth of leaves, bark, and branches. Now multiply that by the thousands of Diprotodons, Pleistocene, Zygomaturus, and giant kangaroos that roamed the landscape. You're looking at an ecosystem where herbivore biomass was incredibly high, possibly higher than in any modern ecosystem, except the Serengeti. But here's the thing. Australia's soils are ancient and nutrient-poor. Unlike the fertile river valleys of Africa or the grasslands of North America, Australian vegetation tends to be low in nitrogen and high in tough, fibrous material. This means herbivores had to process massive quantities of low-quality forage just to meet their energy needs. And that, in turn, limited population densities and created bottlenecks during dry seasons or droughts. So the megafauna of prehistoric Australia were living on the edge, ecologically speaking. They were surviving, yes, but they weren't thriving in abundance. They were maximizing every calorie they could extract from a relatively unproductive landscape. And that brings us to the predators. Because in an ecosystem where herbivore populations are limited by food availability, predator populations are even more constrained. Thylacoleo probably existed at very low densities, maybe one individual per several hundred square kilometers. It couldn't afford to hunt recklessly or expend energy chasing prey across long distances.
As you can see,
Instead,
the extinction
it had to be a
event
patient,
correlates strongly
efficient killer,
with the younger drivers.
ambush predation,
But
calculated
the human
strikes,
dispersal data
maximum lethality with minimum energy expenditure. And that's why Thylacoleo evolved such extreme killing tools. In an environment where every hunt mattered, evolution favored the most efficient killing machines. But Thylacoleo wasn't the only predator to worry about. Now, here's where prehistoric Australia really earns its reputation as a death trap. Because on top of the marsupial megafauna, you also had reptiles. Big ones. Meet Megalania, or as it's now officially known, Varanus priscus, the largest terrestrial lizard that ever lived. Conservative estimates put Megalania at about 3.5 meters long and 200 kilograms. More aggressive estimates go as high as 7 meters and 620 kilograms. Though most paleontologists consider those upper estimates unlikely. But even at the conservative end, Megalania was a monster. For context, the Komodo dragon, the largest living lizard, maxes out at about 3 meters and 90 kilograms. So Megalania was at minimum twice as heavy as a Komodo, and possibly much larger. And here's what makes Megalania truly terrifying. It was almost certainly venomous. Modern monitor lizards, including Komodos, possess venom glands that produce toxins, affecting blood clotting and blood pressure. A Komodo bite delivers these toxins deep into prey, causing rapid blood loss, shock, and eventual collapse. Megalania, as a close relative of modern monitors, likely had even more potent venom. Combined with its size and a mouthful of serrated, recurved teeth designed for slicing flesh, Megalania was a walking nightmare. Think about how it hunted. Unlike Thylacoleo, which relied on explosive ambushes, Megalania was probably a persistence predator. It didn't need to kill immediately. It just needed to land one solid bite. After that, it followed, patiently, waiting for the venom and blood loss to do their work. Hours, days, however long it took. Eventually, the prey would weaken, collapse, and Megalania would move in to feed. But here's the kicker. Megalania wasn't restricted to the ground. Monitor lizards are excellent climbers and swimmers. Megalania could hunt in trees, along riverbanks, and across rocky terrain. There was no safe refuge. And Megalania wasn't the only giant reptile. There were also giant snakes, pythons reaching lengths of 5 to 6 meters, and massive freshwater crocodiles in the northern river systems. So let's take stock. If you're an animal living in Pleistocene Australia, you're dealing with Thylacoleo, a hypercarnivorous marsupial with bone, crushing jaws and grappling claws, Megalania, a venomous lizard the size of a grizzly bear that could track you for days, giant pythons that could constrict prey the size of a human, freshwater crocodiles up to 5 meters long, you'd kick with enough force to shatter bones. And you're doing all of this in an environment with limited water, unpredictable food supplies, and regular droughts. So here's the question. How did anything survive? Well, the answer is barely. And only the most perfectly adapted species made it. Let's look at the herbivores for a moment. Because these animals weren't just passive victims. They evolved defensive strategies that made them incredibly difficult to kill. Diprotodon's primary defense was simple size. At 800 kilograms, a healthy adult Diprotodon, was essentially immune to predation by anything other than the largest Megalania, or a coordinated attack by multiple Thylacoleos. But size comes with costs. Diprotodon was slow, probably moving at a walking pace of 3 to 5 kilometers per hour. It couldn't run. It couldn't climb. If threatened, its only option was to stand its ground or flee to water, where its bulk might provide some protection. Short-faced kangaroos, on the other hand, combined size with mobility. They couldn't hop as fast as modern kangaroos. Their legs were too short and their bodies too heavy. But they could still move quickly over short distances. And those powerful forelimbs with elongated claws. Perfect for defense. A swipe from a Procoptodon could seriously injure a predator. Then there's Pleistocene, with its long, flexible snout and massive claws. Pleistocene was probably adept at manipulating its environment. It could pull down branches,
or marsupial
dig for roots, and potentially fend off attackers by rearing up and slashing with its forelimbs. But here's the thing. All these defensive adaptations required energy. Energy that came from food. And food, in Pleistocene Australia, was never guaranteed. During good years with regular rainfall and abundant vegetation, the megafauna thrived. Birth rates increased. Juveniles survived to adulthood. Populations grew. But during bad years, droughts could last for years. Water sources dried up. Vegetation withered. And the megafauna, with their enormous caloric needs, suffered catastrophically. This is where size becomes a double-edged sword. Yes, being large protects you from predators. But it also means you need more food, more water, and more space. And when those resources disappear, large animals are the first to starve. Scientists call this the megafaunal paradox. The very traits that make you dominant during good times make you vulnerable during bad times. And Pleistocene Australia was a land of boom and bust. Long periods of stability punctuated by droughts, fires, and climate shifts. The megafauna had survived this for millions of years. They'd evolved behavioral strategies, migration routes, water, finding abilities, drought resistance, that allowed them to persist through even the worst conditions. But then something changed. Something that the megafauna had never encountered before. Something that didn't just hunt them, but fundamentally altered their environment in ways they couldn't adapt to. Humans arrived. Tufan Fie CT3. Tiachi call la PC off NT. Here's where the story of prehistoric Australia takes a tragic turn. Because around 65,000 to 50,000 years ago, the exact date is still debated, modern humans arrived on the Australian continent. These weren't the first hominins, but they were the first Homo sapiens. The first species with advanced cognitive abilities, sophisticated tools, and, most critically, the ability to use fire systematically. And within a geologically instantaneous period, maybe 5,000 to 10,000 years, the megafauna began to disappear. So here's the question everyone wants to know. Did humans cause the extinction of Australia's megafauna? Or was it climate change? Or some combination of both? Well, the answer is complicated. And scientists are still debating the details. But the evidence increasingly points toward human activity as the primary driver. Let me explain. And first, let's look at timing. Fossil evidence shows that the megafauna had survived multiple cycles of climate change over millions of years. They'd endured ice ages, droughts, and shifts in vegetation patterns. These were resilient species, adapted to Australia's harsh and variable environment. But they'd never encountered humans before. Archaeological evidence shows that humans arrived in Australia during a period of relative climate stability. Yes,
Good heavens.
the continent was gradually drying, but no more so than it had during previous interglacial periods. Yet within a remarkably short time after human arrival, megafaunal species began going extinct. Diprotodon, Thylacoleo, Megalania, Geniornis, Pelorchistis, the giant kangaroos, all disappeared within a few thousand years. Second, let's look at the pattern of extinctions. It wasn't random. The species that went extinct were almost exclusively large-bodied. Animals weighing more than 45 kilograms. Smaller species survived. This is called size-selective extinction, and it's a hallmark of human-caused extinctions worldwide. Large animals are easier to hunt, provide more calories per kill, and reproduce more slowly, making them vulnerable to even moderate levels of hunting pressure. Third, there's the fire evidence. Humans in Australia used fire extensively, for hunting, for clearing land, for encouraging the growth of certain edible plants. This practice, known as Prehistoric farming, fundamentally altered Australia's vegetation patterns. Charcoal records from sediment cores show a dramatic increase in fire frequency and intensity starting around 50,000 years ago, right when humans arrived. Now, here's why that matters. Australia's megafauna were adapted to a landscape shaped by natural fire regimes. Fires sparked by lightning, burning in predictable patterns, leaving large areas of mature forest and diverse vegetation. But human-caused fires were different, more frequent, more extensive, more destructive. The result? A shift from closed, canopy forests and woodlands toward more open, fire-adapted landscapes dominated by grasses and fire-resistant shrubs. For browsers like Diprotodon and Pelorchistis, which relied on woody vegetation and forest edges, this was catastrophic. Their food sources disappeared, their habitats fragmented, and they had nowhere to go. Even if humans never directly hunted these species to extinction, the landscape, level changes caused by fire would have been enough to push them over the edge. Cascading Collapse. But here's where it gets really interesting. Because the extinction of the megafauna wasn't just a loss of individual species. It was the collapse of an entire ecosystem. Think about it this way. Diprotodon wasn't just a herbivore. It was an ecosystem engineer. A 800-kilogram animal moving through the landscape, trampling vegetation, creating trails, dispersing seeds, fertilizing soil with its dung. When Diprotodon disappeared, all those ecological functions disappeared with it. The same goes for the giant kangaroos, Pelorchistis, and all the other large herbivores. They were maintaining the landscape, keeping vegetation in check, creating habitat heterogeneity. Without them, the vegetation structure changed, fire regimes intensified, and the remaining species, those that survived, found themselves in an ecosystem that no longer functioned the way it had for millions of years. And then there's the predators, Thylacoleo, Megalania. These were apex predators that regulated herbivore populations and maintained ecosystem balance. When their prey disappeared, they starved. Simple as that. Thylacoleo might have tried switching to smaller prey, wallabies, wombats. But a 150-kilogram predator can't sustain itself on animals a tenth its size. The energy math doesn't work. It needed large prey, and once that was gone, Thylacoleo was doomed. The same goes for Megalania. A 200-kilogram lizard needs enormous amounts of food. Without access to megafaunal carcasses and large prey, it couldn't survive. So what we're looking at isn't just hunting. It's a cascading collapse. Humans altered the landscape with fire. That reduced megafaunal populations, which removed ecological engineers and prey species, which caused predators to starve, which fundamentally restructured the entire ecosystem. And once the collapse started, there was no stopping it. So if the megafauna were so perfectly adapted, so dominant, so seemingly invincible, why couldn't they survive? Well, the answer is both simple and tragic. The world changed too fast, and they couldn't adapt. See, evolution is slow. It works across thousands of generations, making incremental adjustments to changing conditions. The megafauna had millions of years to adapt to Australia's climate, vegetation, and fire regimes. But humans didn't just change the environment, they transformed it. Within a handful of generations, the landscape looked completely different. The fire frequency doubled, tripled. The vegetation shifted. The prey networks collapsed. And there simply wasn't enough time for evolution to respond. Diprotodon couldn't evolve a faster reproductive rate. Thylacoleo couldn't evolve to hunt smaller prey efficiently. Megalania couldn't shrink to match the new food availability. They were locked into body plans and ecological strategies that had worked for millions of years. And when those strategies stopped working, they had no backup plan. This is the harsh reality of extinction. It doesn't matter how successful you were in the past. It doesn't matter how well adapted you are to your environment. If that environment changes faster than you can adapt, you disappear. And this pattern, the extinction of megafauna following human arrival, isn't unique to Australia. It happened in North America, in South America, on islands across the Pacific. Wherever humans arrived, the megafauna vanished. Australia's story is unique only in its extremity, because nowhere else did evolution produce such bizarre, specialized, and ultimately fragile giants. Prehistoric Australia was a world that should never have existed. It was too harsh, too unpredictable, too hostile to support the kinds of massive herbivores and hyper-carnivorous predators that dominated the landscape. But for millions of years, it did, because evolution had time to experiment, time to refine, time to create perfectly calibrated survival machines that could extract just enough energy from an unproductive landscape to persist. And then, in the blink of an eye, it all ended. Not because of a meteor, not because of a volcanic eruption, but because one species, Homo sapiens, arrived with a new technology and a new way of interacting with the environment. We didn't set out to destroy the megafauna. We were just trying to survive, to find food, to shape the landscape in ways that made hunting and gathering easier. But the consequence was total ecosystem collapse, the loss of species that had existed for millions of years, the simplification of one of the most complex and unique biomes on Earth. And here's the thing that should make us uncomfortable. We're still doing it. Right now, Today, the forces that drove the megafauna to extinction,
This incredible flexibility
habitat
is key to the
destruction,
python's predatory
climate change,
success. The lower jaw
ecosystem
bones are
fragmentation
not used.
are the same forces threatening modern species worldwide. The difference is, now we know. We understand the consequences. We can see the pattern. So the question is, will we choose differently? Prehistoric Australia was a land where survival was impossible, for the megafauna at least. For us, it became a conquered landscape, an emptied stage. But it didn't have to be that way. And it doesn't have to be that way going forward. The giants are gone. The marsupial lions, the thunder lizards, the 10-foot kangaroos. They exist now only as bones in caves and museums. But their story isn't just about the past. It's a warning about the future. Because if we're not careful, we'll keep emptying the stage. Keep simplifying ecosystems. Keep removing the irreplaceable. Until one day, we look around and realize we're the only megafauna left. And that's a world none of us should want to live in. PTOPTIL. MIBARSUBCTAC. Asking for support always feels a little awkward, so I'll keep this brief. Creating these videos is a labor of love. That's why I want to push the boundaries of what this channel can be. Richer visuals, deeper research,
The Thylacoleo
and stories
or
that truly
Marsupial
spark
line
wonder.
possess these massive
But quality
specialized
takes time,
like premolars.
and it's hard to do this alone. That's why I'm launching channel memberships. By becoming a member, you aren't just donating. You're buying me the time to craft bigger, better films. So, if you believe in this mission and want to help me keep exploring the unknown, please consider clicking the join button. I literally exist because of you. Thank you. And until next time, you can watch this video here. I think you'll love it. Fashi NDFF say word total word count 11,400 words. Estimated runtime 35-40 minutes.